when I was preparing for my uniform acceleration presentation, I stumbled upon something that blew my mind. I remember vaguely being introduced to it 12 years ago when I studied physics, but I must have let it slip my mind. It's called the Unruh effect, and it's pretty weird stuff. It has to do with counting particles and how the cardinality of particles is relative. I must warn that the concepts here are a bit heavier than the concepts in my uniform acceleration presentation, so you've been properly warned. First off though, while the uniform acceleration I presented earlier was pure relativity, this effect is in the intersection between general relativity and quantum field theory. Now you may have heard that there's no theory combining relativity and quantum theory that has been developed, and in one sense that's true, though string theorists and loop quantizers may not agree. More precisely, describing general relativity using a quantum theory has not yet been performed, at least not convincingly. However, as long as you want to describe quantum fields in a general relativity setting, that is possible, and basically that's why you may have heard about Hawking's and Penrose and the like. There's a book called Quantum Fields in Curved Spacetime by Burrell and Davies that describes this. I borrowed it and tried reading it, but with the time and energy I have right now, this task is a bit daunting. So I will instead describe the effect using a popular science approach. So there will be plenty of opportunity to arrest me for the way I present things here. Anyway, consider an inertial, that is a non-accelerating observer, as in special relativity. Let's say that he is in deep space and measures the particle number, and he finds out that he is in a vacuum. There is no real particles. Then he switches on the rocket engines, and more or less at once he starts observing particles. He now finds out that he is in a thermal bath of particles with a temperature T equals to h bar times the acceleration divided by 2 pi c times k. So the number of particles has changed simply by going from one relativistic system to another. A qualitative explanation for this is that the particle number operator is not preserved under relativistic transformations. When you go from an inertial system to an accelerated one, you will have a different quantum number of particles operator with different states, and you will just get different observations. But that's a rather abstract way to look at it, so let's go to the popular science approach. In quantum theory, you have the so-called Heisenberg's uncertainty principle, which states that you cannot measure the momentum and position to a combined accuracy of more than h bar half. Alternately, you cannot know the energy and time interval of the same event to a precision of more than h bar half. This can give a picture of what happens in a quantum field theory where the number of particles is not fixed. This is often called quantum foam. Basically, you can picture a vacuum as consisting of pairs of particles, particle and antiparticle, that comes into existence and annihilates in such a way that you cannot do direct measurements on them. These so-called virtual particles live in the realm where delta E times delta T is less than or equal to h bar half. While this can seem thoroughly like fantasy, quantum field theory yields predictions that have been confirmed to a startling precision. Also, the Casimir effect is an absurd phenomenon that can be described by using virtual particles. Virtual photons will have a wavelength of c times delta t in that brief time, which will be the uncertainty in their position. Basically, what you will get here is that some of the virtual particles in an inertial system are real particles in an accelerated system. Anyway, from the last part of my uniform acceleration presentation, you may recall that an accelerated system has an event horizon behind you at a distance of c squared over g. Now consider a virtual particle pair that comes into existence on the event horizon of an accelerated system, and which have a wavelength equal to c squared over g. Since the pair of particles may be separated with that much distance, one of them might be in the vicinity of the rocket ship, while the other might be on the wrong side of the event horizon, and will thus not be able to annihilate with the other particle. Without that annihilation, the other particle can be viewed as a real particle, which will be able to interact with the spaceship. The more acceleration, the shorter the characteristic wavelength of this radiation, and the shorter the wavelength, the more energy, and thus also the higher the temperature. So the temperature will be proportional to the acceleration. And the formula I have derived here is the correct one, though with only dimensionality arguments and semi-classical approach, this has to be a fluke. I must hasten to add that this is not the real description of this theoretical phenomena. The real description involves general relativity metrics and quantum field operators and states, and is a little bit beyond me right now. I should also mention that for daily life acceleration, this effect is extremely small. Under an acceleration of 1g, you'll get photons with a characteristic wavelength of 1 light year, with a frequency of about 1 per year, according to dimensionality arguments. So anyway, good luck keeping up that acceleration for 1 year, by the way. According to the Wikipedia article, an experiment checking this effect under extreme acceleration is planned. If it succeeds, we may have the first experimental data for a combination of quantum field theory and general relativity. Anyway, it gets you thinking, doesn't it? If the number of particles is a relative quantity, and thus two people counting particles will not agree simply because they move in a different manner, how certain can we be that other real-world concepts have absolute cardinality, when this is the most fundamental of concepts, that of a particle, do not? I don't know. Hope it was interesting anyway. Bye for now.